In this video, I want to derive the mirror equation. So what is a mirror equation? Some of you might know what it is, and some may be hearing it for the first time. Since it has the word mirror in it, let's first draw a mirror. Should we draw a concave mirror or a convex one? Well, the mirror equation works for both. But let's start with a concave mirror. You are already familiar with all these symbols. P is the pole, C is the center of curvature. It is the center of a sphere of which the reflecting surface is a part of. The midpoint of C and P is the principal focus F. And finally, the line which joins all of them is the principal axis. Suppose that our object is kept behind C at a finite distance away from the mirror. We draw our usual diagram to get the image, which is of course a real image. So what is a mirror equation? Well, let me just write it down first. 1 over F is equal to 1 over U plus 1 over V. What do these three letters symbolize? They're nothing but distances between points. To understand better, let's draw a tangent at point P like this. In this equation, U is the distance between the object and the mirror. So this distance will be U. It is the distance between points A and P. Remember, the distance between two parallel lines will always be the same. So this distance is nothing but distance between points A and P. V is the distance between the image and the mirror. Let's name this point G. So V is nothing but the distance between points G and P. And F is the focal point, which is the distance between the principal focus and the pole. This distance is equal to F. Note that all the distances are measured from the pole of the mirror and not some other point on the mirror. So from the equation, you can see that it gives us the relation between the object's distance from the mirror, image's distance from the mirror, and the focal length. What if instead of this, I had placed an object somewhere else? It wouldn't change our formula. The equation does not depend on the object's position from the mirror. It is same for any position of the object. What if instead of concave mirror we had convex mirror? Again, it wouldn't change our formula. Yes, this formula is true for all types of spherical mirrors, convex as well as concave mirrors. Now the question is, how do we derive or prove this formula? There are many ways to derive the equation, but we will look at the easiest one. In order to derive this formula, we need to know only one thing, and that is the concept of similar triangles. You must have come across similar triangles many times in our math class. So let's review that first. In simple language, triangles are said to be similar if they have the same shape. For instance, these two triangles are similar since they have the same shape. This triangle is just a scaled down version of this. These two are also similar triangles. What's so special about similar triangles? When two triangles are similar, then the ratios of their corresponding sides are equal. For instance, here triangle ABC and triangle PQR are similar, so AB over PQ is equal to BC over QR is equal to AC over PR. And this fact is going to help us derive the mirror equation. The second thing about two similar triangles is that all the corresponding angles have the same measure. For example, here, angle A is equal to angle P, angle B is equal to angle Q, and angle C is equal to angle R. This also works in the reverse. That is, if for any two triangles, if we prove that their corresponding angles are equal, then they are similar triangles. This is called AAA test of similarity for proving two triangles similar. Similarly, if the ratios of their corresponding sides are equal, then the triangles are similar. Okay, let's go back to our figure for the mirror equation. Now from the top of the object, let me draw a line that meets the tangent at point B. This line is parallel to the principal axis. And from this point on the image, let me draw a parallel line again to the tangent at point D. Note that points B and D are not on the mirror. They're on this tangent which is drawn at point P. But actually, both the points are very close to each other in reality. This is because we have seen in our previous video that the aperture of the mirror that we are considering is much smaller than the radius of curvature. Because of the smaller aperture, these distances are very small, and so we can assume these 2 points to be on the tangent. So we can assume these 2 points to be 1 point and these 2 points to be 1 point. Now consider these 2 triangles. Are these 2 triangles similar? Let me first just draw them separately here. We see that angle OAF is equal to angle DPF. Why? They both measure 90 degrees. What about these 2 angles? Angle OFA and angle DFB? When 2 lines intersect, the vertically opposite angles are always equal. Hence, these 2 angles are equal too. What about the remaining angles? How do we show that they are also equal? With very basic logic, we know that if the 2 sets of corresponding angles are equal, then the third set has to be equal. Finally, we proved that triangles OAF and DPF are similar by the AA or AAA test of similarity. Now, because they're similar, we can say that OA over DP is equal to AF over PF is equal to OF over DF. We're not really interested in this ratio, so we will just remove it from here. Now, from this figure, can you tell me what AF and PF represent? PF is the focal length F, but what about AF? We know that AP is the object's distance from the mirror, which is U. But AP is equal to AF plus FP, and FP is the focal length F. So AF is nothing but U minus F. And what are OA and DP? They are the heights of the object and the image. Let's denote them with HO and HI. We're not done yet. This is not the formula that we're looking for. Let this be equation 1. Now consider triangles IGF and BPF. These 2 triangles are also similar again by the AAA test. I will leave this for you to verify. The ratios of their corresponding sides are equal. I will remove this ratio as it's not required. IG and BP are nothing but the heights of the image and the object. PF is the focal length F. So what's GF? GP is equal to GF plus FP. We know that FP is F. So what's GP? Yes, it's the image's distance from the mirror V. Therefore, GF is V minus F. Let this be equation 2. Now let's invert equation 2 to get the third equation. We are almost there now. So we have these 2 equations now with us. They both have the same term on one side of equal to sign, so the other 2 sides will be equal. Cross-multiplying and solving further will finally give us the required mirror formula. Finally, we have our mirror equation in front of us. It was fun to derive it, wasn't it? However, this is not the only way to derive the mirror equation. Now, if you remember, at the start of the video, I told you that this is a general equation. That is, this equation is valid for any position of the object and for any spherical mirror under consideration. But is it so? In order to use this equation, we must make sure that some rules are followed. We will see those rules in our next video.